Hello and welcome back. We are talking about section 4.2, logarithmic functions. This video we're going to try to tackle, in particular, use logarithms to solve exponential equations. So let's get there. Okay, so just a note before we jump in. I think of using logarithms to solve exponential equations as kind of the main point of logarithms. There certainly are applications that involve logarithmic functions just by themselves, but for the most part, the story of logarithms is a way to undo exponents, and so this is precisely what we'll employ them for most frequently. So in this example, we've got kind of a compound interest setup, so we have an investment. We'd like to figure out how long it will take to triple that investment if interest gets compounded monthly and it's at a 4.5% nominal annual interest rate. So you might notice we don't actually have a principal value for this, but that shouldn't actually set us back too far. So let's just call it something generic like p for principal. And we know our interest rate as a decimal is 0.045. We know that k is 12 because that's how many times interest is compounded per year. And then we've got a formula that tells us the value of that investment after t years have gone by. So we don't have a value for p. It turns out that's not going to be that big of a stumbling block. The other things we know, with the exception of time, which is exactly what we're looking for here. We're asked to find tripling time, basically. Okay, so the target investment is triple our starting investment. So if our initial investment is p, then our final investment is going to be 3 times p. Usually that would be an issue, but if you notice, the first thing that we would try to do to solve is that we would divide both sides by p. And in doing, innocently or otherwise, sure, we get rid of it here, but it also cancels this principal out on the right side. So we're left with just 3 equals this expression, and now you might notice that the only variable in this equation is t, and that's precisely the thing we were trying to find. So at that point we can use any kind of logarithm, but natural logarithm is sort of convenient because it's only 2 letters to write instead of log. All we have to do is write ln. No, that's not the best reason, but it is a reason. So natural log we can use, or any other flavor really. And then, as mentioned, we use that power rule for logarithms. So if you have natural log, or any kind of log, of something raised to a power, then this power gets to come down as a multiple out in front. And that's precisely why we would take this logarithm, is to bring that value out in front. So now we have the variable down on the ground floor. So this is a great place to be. Now we have 12 times t times another number, even though this is a weird number, it's just a number. And we can divide out all that constant stuff. Divide both sides by 12 and by natural log of 1.0, etc. So then our t value is this exactly, and approximately 24.46. But remember that interest only gets compounded monthly anyway, so we could only do this, we could only pick basically between month 5 or month 6. So if we wanted to exceed triple our initial investment, we'd have to go out to the full half year and say 24 and a half years. That's certainly not going to be a matter of an issue of taking off points on a test, but it's something to think about, that this really is kind of a discrete thing that we're working with. We could move from May to a June investment, and that's basically our choice. Okay, so sometimes it's convenient to write a logarithm in some other form. So for instance, the most common time this comes up in the age of graphing calculators or scientific calculators is that for some reason I end up wanting to compute something like log base 2 of 5. And then I go to my calculator and I realize that there's no log base 2 button or base anything button. So I need to convert it to something that my calculator is capable of handling. So the two things that most calculators have on them as far as logarithms are concerned is a log, a common log base 10 button, and then a natural log button. And we're going to choose the natural log button since that tends to be the favorite as far as bases are concerned for logarithms. So just a quick implementation of this. For instance, if we somehow ended up in an expression with log base 8 of 15, most modern calculators would have a hard time evaluating this. Of course, things like Wolfram Alpha and other computer algebra systems don't really have this weakness, but this is something that handheld calculators are still not especially good at. So the way that this gets modeled, and my mnemonic for this is basically the following. I imagine I've got 2 things that are being worked out here: the actual argument, the input of this logarithm, and its base. The one that's physically higher is the one that gets shunted into the top here. and the one that's lower gets dumped into the bottom. So I'm going to take any flavor of log, any kind of log we want, but natural log seems to be a logical choice, and we have to pick the same for the top and the bottom. So what you might notice in a calculator is that these two numbers, the top and the bottom, are very different from what you get if you look at different kinds of logs, log, common log of 15 versus common log of 8. But once you divide them, you get the exact same answer for between these. So it doesn't matter what kind of log we pick for numerator or denominator, as long as they're the same. Okay, so there's the conversion formula, sometimes called change of base formula for logarithms. So let's do one more application. So we've got some cesium-137. It's been reserved for cancer treatment, but it hasn't been used in that time. So 2.2 years have gone by. And the folks in charge of this sample have noticed that 5% of that original sample has decayed into other things besides this radioactive isotope. So the question is, what is the half-life? And that's a piece of terminology, so it's in bold there. The half-life is the time required to reduce some radioactive substance to half of its beginning quantity. So our job is to figure out that length of time. Okay, so we could begin with any kind of exponential model to work with. I'll just pick the e to the something model for variety. It would have been perfectly valid to pick, even if we went exciting like q naught for this initial quantity, to go with this b to the t kind of model. So this is exactly the same thing. In fact, it's just that e to the negative k in this case would fill the same role as the constant b. But just for variety, and because oftentimes these kind of models are written with an e base, we'll try this version out. So remember, the information we've been given is that 2.2 years down the line, 95% of the original samples left. So don't get caught putting 5% in for Q. It's not that 5% remains, it's that 5% went away. So the quantity remaining would be 95% of whatever our starting value was. So we can use this value to find out the unknown constant K. So this initial sample, or initial piece of information we've been given, that 2.2 years go by and we're left with 95%, helps us figure out this unknown constant. Okay, so just like that tripling time example, basically we're using this to find this k value, but we're saying, okay, this is the 95% time, if you will. So 95% of whatever the starting quantity looked like. Again, it doesn't matter how much was there to begin with. So dividing both sides by q naught, where we have that constant disappear from the mix, and the only thing that remains is k in this equation. So taking natural logs of both sides, in this case, you don't even have to worry about the power rule for logarithms. Sure, this thing would come down, but even better, taking natural log of e to the something, natural log of e to some power, those things cancel each other out perfectly. So we're left with just this exponent. So the only thing that remains once we take natural logs of both sides is that piece, which is perfect because that's going to help us solve for k. Last thing to do is divide by negative 2.2 and get ourselves a constant. Okay, so this is just the first step of this. The only reason that knowing k is worthwhile is that now we have an actual equation for our cesium quantity that remains, and we can use this to solve for the stuff set equal to 0.5. Okay, so now we're actually going to get down to the real question here, figuring out what this half-life is. So we're going to pick a kind of particular time to look at. We'll call it h. It's this unknown value, h for half-life, I guess. And basically what we're looking for is for our output to be 0.5 of our starting quantity. So this is going to look a lot like what we did before, just a minute ago. But remember, this is not repeating ground because now we've actually got a value for k. Instead of having an unknown constant there, we know everything in this equation except for h. Or at least once we divide out q naught, we will know everything except for h. So divide out that initial quantity. We've got a very familiar equation, and we do the same thing we did a minute ago. We take natural logs of both sides because that's going to help us pop this exponent out of that position. Natural log of e to the stuff is just stuff. So the last thing to do would be to divide by negative 0.02, etc., and get ourselves 29.75. So the one caution is to hold on, if possible with computation, hold on to as many of these decimal places from our k calculation a minute ago on the previous slide where we actually figured out the value of k. Remember, because we're dealing with logs, the odds are good that this is actually a totally irrational number, that these decimals keep repeating. So there's as much accuracy as we could possibly try to grab from decimals out there. That will make this answer more accurate if we don't round this terribly much. But either way, we get a conclusion that CC-137 has a half-life of about 30 years. In actuality, it's about 30.17 years, but that's where sensitivity, not just to our calculations, but also to the original measurements that would have been involved in seeing how much of the sample remained. That's it for this video and for 4.2. We'll be back with the next section in the chapter.